means I'm integrating over an entire surface. I'm taking some closed surface in space and integrating over the entire surface, right? That surface, by definition, because it's closed, encloses a certain amount of space. If there is charge in that space, that's what Q enclosed, right? So Q is enclosed by this surface over which I'm integrating. That's why we say it's enclosed. And the integration symbol just tells you to integrate over the entire thing. Okay, something similar is happening here. This is a one-dimensional integral, though not an area integral. This is a line, but this tells you it must be a closed line, right? Not a closed line, a closed line. So you're integrating around a line which necessarily bounds an area. Through that area may or may not be flowing a current. Right? If there is one, if there's a current flowing through this bounded area, that's what goes in here as I enclosed. Notice the similarities though. I'm integrating a field dotted into a spatial variable. Right? The field integrated over this line. The field integrated over this area. Equals the enclosed whatever I care about. If I care about just charges, it's there. If I care about moving charges, it's here. And then there's the first principal variable. Electric permittivity, magnetic permeability. Right? These are very, very similar. Notice the constants appear in different places. This is in a numerator. This is in a denominator. We've seen that before, so we're going to see it again. This is normal. Okay. This is Ampere's law. How does that function? Well, let's see. Let me take a current, right? There's a current, I, and let it come out of the page. If I would like to determine the electric field, magnetic field due to this current, and I'm going to do an Ampere's law here. I'm going to ask myself the same sort of questions I asked myself with Gauss's law. Is the geometry simple, right? What that meant for Gauss's law is this dot product really easily evaluable? And we figured out that it's easily evaluable when it's perpendicular, I should say these two vectors are perpendicular, or when they're parallel. When they're perpendicular, it gives you 0. No, sorry, when they're perpendicular, it gives you EDA. When they're parallel, it gives you 0. Right? Back. When the electric field is perpendicular to the area, what that means for the vectors is that the vector area, the area vector should say, is parallel to the vector. Let me rewind and back that up. Okay, let's do that again. This is easily evaluable when these vectors are parallel or perpendicular. If the vectors are parallel, it gives you EDA. If the vectors are perpendicular, it gives you 0. The reason that's confusing is because for these vectors to be parallel, that means the electric field is perpendicular to the area. There's the area. There's the area vector, right? If this then is the electric field, see, the electric field is perpendicular to the area, but that means it's parallel to the area vector. And that's what makes a difference. Okay. If it's 0, use it. If it's perpendicular, use it. Other than that, it's probably not easier. Same thing here. This is easily evaluable if B and BL are parallel or perpendicular. If they are not, it's probably not easier to use Ampere's law than the Biot-Savart law. But in the cases where it is, this works really well. Okay. Let's see what we come up with here. Let's figure out what sort of Amperian loop, right? We had a Gaussian surface, now we have an Amperian loop. A loop because I got to make it closed. What sort of Amperian loop is going to match this geometry? Hopefully, it's probably easy to see that a circle. If I make an Amperian loop like this, see if it meets my criteria. Closed loop? Yes. Geometry simple? Yes. Do I have to make it like this? No. But it's easier if I do. Okay. Now, we're going to rely on some previous work because we've already been able to measure our magnetic field and notice that it is always tangent to a circle surrounding them. So, let's do this. start our integration, we're going to go from this point around, we're going to integrate that. That means my DL at any point is going to be tangent to that circle. Okay. Well, any magnetic field that's going to contribute to this is going to have a component parallel to this. The parallel component is what's going to matter because the dot product is going to kill off anything else. So pick whatever magnetic field you want to. Maybe this one, right? Any component of this perpendicular to this will not survive the dot product. But anything parallel will be kept by the dot product. So let's see what that gets us. First of all, do I have a current enclosed by this particular Amperian loop? Not a rhetorical question. Yeah, I do. It's this one, right? I've enclosed it. Okay, fair enough. Now, just like with Gauss's law, I didn't ever actually integrate, right? I never really integrated the left-hand side. It's a simple integration, EDA. The reason I'm using it is because E is constant over that surface, and dA is the value x to A. Something similar is going to happen here. Because I've centered my circle on my wire, and because I know that the magnetic strength is a function of distance, as long as I stay the same distance away from my current, the magnetic field is going to be constant in magnitude. So that means it can come out of the integral. In other words, when I perform the dot product, I just get BDL, just like I got EDA. And B is going to be constant because I've centered my circle on the source of the field. So this is going to reduce to B integral DL equals mu naught, and I enclosed, I've just called it I. Now, integral of DL is what? Yes, but that's my next step. Integral of DL is just L, right? Easiest integral you're going to do. What is the length of that circle? Or I should say, what is the length of that dashed line? 2 pi r, right? Just the circumference of the circle. So I have constructed my circle, which I forgot to put here, at some distance r. Just like I constructed my area at some distance r. It's important to have this as your variable, because what we're finding is the electric and magnetic fields everywhere. So that's my distance r. So this just reduces to V times L, but L in this case is 2 pi r is equal to mu naught I. Divide through to get the magnetic field. B is equal to mu naught over 2 pi r, which is the exact result we got from the Biot-Savart law. Through a heck of a lot more work, right? We got a lot of work to do on that one. But this one, it just kind of falls out at us. That's nice, because it happens because the geometry is simple. So we've derived a result we already know, but we got it a lot easier. Okay? Questions about this?
What happened to the I enclosed?
Well, I enclosed, I just called it I. Right? So, good question. This is a general formula, right? This is whatever I'm enclosing in my Amperian loop. When I constructed my Amperian loop, I figured out that I actually enclosed this thing that I called I. See right there?
So for the final equation, when you did B equals, okay.
Thank you.
All right.
I see what you, yeah, I just love talk.
All right.
Thank you. Yeah, you gotta have a source if you're gonna have a field. Right. Okay, other questions? Okay. Ampere's law is not something, like I said, we're going to go into a whole lot. If you have more E&M in your future, you'll use it a lot. But I'm going to have your TAs do an example tomorrow in the lab using a solenoid. So we'll talk briefly about what a solenoid is, because they become important. A solenoid is basically a large collection of loops of currents. So, if I take a wire and I form it into a helix, and then I let some current run through it, right? So the current's running through the wire. At any given point along this helix, I mean, you can see the current is going in a circle, but it's also going up, right? So at any given point, my current will have a vertical component and a horizontal component. It's going to look something, you know, like this as it goes along its way. It would be really nice if we could simplify the geometry. This is what we always do in physics. We look at really complicated systems and we model them as a lot easier systems. So what we're going to do to treat solenoids is to let this helix collapse down into a really tightly wound spiral. Just cool. It's a coil. If you've ever worked with electronics, you've seen coils. You just wrap your wires really, really close together. And that lets us basically say that instead of treating the current vector like this, we're going to treat it like this, right? Where the angle between the current and the horizontal is just tiny. Basically what we're saying is the vertical component here is negligible. Now, is it really? That depends on your real world application. But for the simple model we're going to develop, we're treating a solenoid that is a coil as a stack of independent loops of currents. They can't be independent or else the current would never actually go through the whole coil. But we're modeling them that way. Right? And so a lot of times you'll see these drawn like this. Where what I've done is I've taken a coil and I've cut it right down the middle. And so you're looking at the ends of the wires as they wrap around. And you're considering each of these to be one independent loop of wire, right? Just one circle. Again, not actually the case. There is a component of this current in every wire that goes up. Because we know the current actually spirals upwards, but we're making our circle so tight that we can just ignore that. And now, if you just look at this one, how many turns of wire do I have? 5, yeah. I've got 5 loops here. This one comes out again, comes out again. So, the terminology we're going to use here is the number of turns, capital N for number, is equal to 5. That's a really low turn solenoid. There are other physical parameters I can look at, right? This solenoid has a certain length L, or height, however you want to look at it. We usually use L. So, any particular solenoid will have a number of turns, which is usually listed on the manufacturing specs. It will have a physical distance that it lasts, right? It's a coil, so it lasts for a year. They spread it out over a certain distance. And so, usually how we characterize these is to take the number of turns and divide it by the length of the solenoid to get what we call the number density or the turn density, so number of turns per unit length, which we generally symbolize with a lowercase n. If you've taken chemistry, you've done something similar, right? Where the capital N would be the number of molecules or atoms in a thing, and the lowercase n is the number density divided by Avogadro's number. Now, if you haven't taken chemistry, you'll get it. We're going to do the same thing here. This is just a density. It's the number of turns per unit length. See you later. And this is usually how we... They open the door, didn't come in. Eat in. This is usually how we characterize it. Okay, so we're going to start using solenoids quite a bit. We can talk about the field of a solenoid, though, because we have talked about the number of loops. We've talked about the field of one loop of wire, right? We had some stipulations. It had to be a steady current, and we had to look at the direct middle, right? When we did that, we got that if we had a loop of wire, let your finger, I should have done this backwards. Let me do this way. Yeah. So where this is in front. If I wrap my fingers around the wire, because this is a field rule, fingers go in what's curved, thumb tells you what's straight. As long as it stays the direct center, the magnetic field of this thing goes all the way up. Well, this is just a big collection of loops of wire. So if I do the same thing, if I wrap my fingers around, in this case it would look like this, right? Because the current is coming out of the board and into the board. So I wrap my fingers around the direction of the current, stick out my thumb. I get in the middle of the solenoid. This thing has a big magnetic field that goes down. What about outside the solenoid? That's really interesting. Yeah, oh sorry. So, the assumption we're going to make is that if we're looking at the field outside the solenoid, let's say at a point right here. Let's look at the field outside the solenoid at this point. We're going to make the assumption that I have not drawn this to scale. That is to say, this distance, we'll call it D1, and this distance, we'll call it D2. We're going to make the assumption that D2 is much, much greater than D1. In other words, the core of the solenoid is small, and outside the solenoid, practically speaking, I'm the same distance from this side as I am from that side, right? Practically speaking. What that means is that over here, I get the same, basically, within a good approximation, the same magnitude of field from, say, this particular coil as I do from the one opposite. Let's look at the directions of those fields. For this, let's just look at a tiny little section of this coil. And remember, if you zoom in on the coil close enough, you can treat it like a straight line. It's like we treat the surface of the earth as flat, but really it's the outside of the globe, right? If you zoom in close enough, you can treat these as little sections that are straight wires. So let's use the right-hand rule for fields of a straight wire, right? Thumb into what's straight, fingers tell me what's curved. So if I'm looking at this particular coil, outside over here, I get a field that's going up. Now let's look at the contribution from the opposite one. Thumb goes out of the board. On this side, I get a field that's going down. And because of these approximations that I've made, is that the approximation that this is practically the same distance from this side of the coil that is from the other side. And because the currents in the coil are all the same, that these two fields are basically the same magnitude, just opposite directions. And so the field ends up pretty much canceling outside of the solenoid. Now, in actuality, it doesn't, because these approximations I make are not the actual situation. But what we can say is outside of a solenoid, the magnetic field is really, really mitigated. So basically with the solenoid, the main field, really the only field that matters for most applications, is the field inside. The field outside basically cancels. Questions about that? So, I know at least one of you has worked with electronics in your real life, right? You see coils all over the place, right? Solenoids are ubiquitous. You find them in computer circuits, you find them in windshield wipers, you find them all over the place. Solenoids are really, really important. We're not delving into them to the extent that you will if you need them for your future career, but we do use them a lot. So this is basically our list of approximations and terminologies that we're making for solenoids. Our approximations are always that we look at these as just a collection of individual loops, not an actual helix. The terminology is that it has a number of turns, capital N. It has a turn density, lowercase n, which is the number of turns per unit length. And our other approximation is that the field in the middle is the only one that actually survives. The field outside completely cancels. Other questions? Any questions, I should say. Okay, I'm going to give you what you will derive in your as an example tomorrow before you do your exercise. Field of a solenoid. This mu naught lowercase n I, where again lowercase n is your term density. Your book also goes into toroids, which I am absolutely not going to go into. A toroid is sort of a solenoid put on its side. You can read that section if you want to, but we're not going to do anything. If you have any fusion research in your future, they use toroids a lot to contain fusion plasmas. That's as much as we're going to do with it. Any questions? It's a lot of information, right? Magnetism has a lot of stuff. So if you find yourself sort of swimming in a swirly sea of confusion, you're in good company. We've all been there. It will start to solidify and the problems work. So any questions about any of this stuff? All right. Okay, then let's move on to something very closely related but slightly different. And I should say that, well, I should have said it earlier. This will be the stopping point for your exam on Friday. There's not going to be anything about solenoids on your exam. Basically, what's on the homework you should use as a guide to what your exam will cover. Also, no Ampere's law. So, what you will be responsible for are forces and fields using the right-hand rule. You will be responsible for at least knowing how to directly integrate simple geometries with Biot-Savart law. There's one on your homework. We did another one in class. On your homework is the straight line. In class, we did a loop. Both of those are fair game. And that's really probably what you would expect to be tested over, right? Right-hand rule stuff, forces and fields, and Biot-Savart law. I'm not going to test you over Ampere's law this time. That will possibly show up next time, but maybe not. Questions about that? Yeah.
What did you say for the second part? Like under Biot-Savart law?
Biot-Savart law, we've done two different geometries. We've done straight line. That's one on your homework. We've also in class done an integration around a loop to determine magnetic field at a point in the center. So those would be the two geometries I would expect you to understand. Any other questions? Any questions? All right. So all this stuff will not be on your exam on Friday, but it will be on the next. Okay. So when we did Gauss's law for electricity, right, we invoked the idea of a flux. Anybody remember what a flux is? You can tell me what it is. Rough terms. Not some stuff passing through or existing inside of or flowing through, depending on what the stuff is. Some sort of area, right? The simplest thing to think of, I think, is to imagine a cross-sectional area of a pipe through which water is flowing, and there's a flux of water through the pipe. We talked about flux of light, from my phone. Flux of light is used a lot in astronomy to determine characteristics of stars. But anything that has directed, you can define a flux, right? The electric field is directed, so we had a flux. It's weird to talk about the electric field flowing. It doesn't do that. So electric field doesn't flow through an area. but it's directed through an area, right? Any directed quantity, I should say, you can define a flux for any directed quantity. Magnetic field is no exception. Magnetic field is a directed quantity. So we can define a flux. So let me take a wire. Right? We know the magnetic field of a long straight wire. You know I over 2 pi. We've gotten it from Biosmart, we've gotten it from amperes now. Alright. So, and we know the right-hand rule for field. So let's look at the region above the wire. And let me ask you this, what direction is the field up here? Into or out of the page? Out of the page, right? Thumb goes into what's straight, that's the wire. Fingers tell you what's curved, that's the field. Above the wire, and the field looks like this. Now, the graphics here are going to be really difficult. You have to really think about it. Because if I were to draw this wire looking down the side, right, if I were to draw an edge on, my current would look like this. And I could draw my field, I would draw my field like this. Where are my arrows different sizes? Got a 1/r dependence, right? I can't draw that here, right? Because I'm looking down on these arrows. But you just have to understand that this is the case for that geometry. I just can't draw it. So always remember that there is a distance dependence of these two. All right, now I'm going to take a metal ring. Just metal. Just take a piece of rebar, attach it to itself, and I'm going to let it fall so that it falls straight down. Okay. So let me ask you this. My first question, and I would actually write these questions down. Is there magnetic flux? The symbol for flux is a phi. I'm going to subscript it with a B for magnetic. Usually a capital phi. Magnetic flux is how you say that. Is there magnetic flux through the ring? And y'all tell me, is there? Yep. The magnetic ring is above the wire. I dropped it, so it's got a velocity that looks like that. But the velocity doesn't actually matter for this question. Is there magnetic flux through the ring? Yeah! Magnetic field exists everywhere up there. Just because I didn't draw a symbol in the middle, don't let that fool you. Magnetic field is everywhere. So yes, it's getting through the ring. Now, if I were to turn the ring sideways, would there be magnetic flux through it? Right, it has to be, remember the angle between the two matters. So as the ring is falling, yeah, there's magnetic flux. If I turn the ring sideways, there wouldn't be. It would just be hitting the edge. But as it is, yeah, there's magnetic flux. Sure. All right. 2. Assuming the answer to number 1 is yes, which it is the flux changing? In other words,